Okay, welcome back to ELE 111, week 2 of the remaining spring semester. This takes us through RC and RL circuits with parallel circuit analysis. We will find that it is very similar to what we did last week. We're going to use a lot of the same techniques, and if you start by taking a look at the top of this page, it recommends you do not follow the formulas that are located in sections 3 and 4 of chapter 16 and 17. They are hard to remember, difficult to apply. You'll use the wrong ones at the wrong time. Start again by realizing that all three components, resistor, capacitor, and inductor, are nothing more than impedances. And if you do that, you'll go from this diagram, which has ohms, farads, and ohms. You'll go to the red circuit, which has nothing but ohms all the way across. How did we accomplish that? We accomplished that by calculating x sub c using 1 over 2 pi fc. This is the magic formula that tells us how many ohms will the capacitor resist with. It's not actually resistance, it's capacitive reactance, and when it's combined with resistance, we call it impedance. Okay? So, our goal is to take every circuit, like the one circled in black, take the given frequency of 10,000 hertz, plug it into the equation shown in the green circle, and come up with the answer to the right and add the minus 90 degrees. This is not done sometimes. This is done all the time with capacitors. Go from the premise that everything in this circuit on the right is impedance. So we use boxes instead of resistor, capacitor, and inductor values. We have 2 resistors and 1 capacitor. 2 resistors and 1 capacitor. Yes, we have a 2,000 ohm resistor marked by the black X. We have a 1,000 ohm resistor marked by the black X. And we have a capacitor that's sitting at 1592. And what we learned in chapter 6, a parallel circuit produces a resistance, but this case it's impedance, of less than the smallest element. Well, the smallest element is 1,000 ohms and resistors. So if you can come up with that set of calculations, you're well on your way to step 2. Now, what is step 2? Step 2 involves finding the impedance total. This would be the same in chapter 6, but in chapter 6 we have no capacitors and no inductors. So we are adding total resistance in chapter 6. Once again, remember to put brackets around all your values or errors will occur when calculating phasor numbers. Now, take a look at the equation circled in green and the equation circled in blue. Both of these equations are valuable in this chapter. It depends. What are you trying to solve? Are you trying to solve a parallel circuit with only 2 components, 2 impedances? One could be a capacitor, one could be an inductor, one could be an inductor and a resistor, etc., etc. Well, the green and the blue circled equations are what are required. And again, we are going to, because in the end, ohms is ohms is ohms. They're all treated like ohms. The only difference being resistors get a phase angle of 0, capacitors get a phase angle of minus 90, and inductors, you got it. They are opposite the capacitors. They have a phase of positive 90. So what I want you to do is, if you just look at these slides, if you just look at these videos, you're going to find out that electronics is not a spectator sport, okay? It takes some work, it takes some perseverance to get through. And here's your first chance to show that you have what it takes. Take a look at the green calculation going on down here. We used the big equation because our circuit has 3 impedances within the circuit. Okay? And if you look back, as such, we need the equation that can do 3 or more impedances at one time. Now, you're going to see me work this problem very methodically, very slowly. We're going to see you try to accelerate the curve and make mistakes and screw things up. So, if you just want to do it right the first time, take a look at how I've done it. I've taken the 1 over 2k in the red circle at 0 degrees. And I've taken 1 and divided it by the bracket of 2k angle 0 close bracket. That gives me what's in the blue circle down below, 0.0005 at an angle of 0 ohms. We continue by computing the capacitor at minus 90 and doing the inversion of this. The way that you should think of this is simply type 1 divided by bracket 1592.35 angle minus 90 closed bracket, and you hit the equals key, and what you will see is this number in the second blue box, 000628 at an angle of 90. Again, we do the third component in red over here. In black, sorry. It's just a resistor, 1,000 ohms at 0 degrees. When it gets inverted, it produces the third blue circle, which is 0.001 at an angle of 0. Okay, so we're breaking this down very slowly. Now, once you've broken it down to this level, to get the answer that's down here in green requires you to add only the bottom numbers with the proper phase angles and the brackets, and you too can score 0.001626 at an angle of 22.717. When you do that long division successfully, you will then end up with the final answer for impedance, which is 614.947 at an angle of minus 22.72 ohms. This tells us that we have 3 components, of which one of them is probably 1,000 ohms. Let's go to, so our answer of 614.947 makes great sense. So, what have we learned in this first calculation? Parallel circuits are no joke. They are a lot harder when doing this equation. If you miss one bracket, if you screw up one sign, everything breaks down. The good news is both series and parallel circuits both can be computing ZT as a step in the solution, step 2 in this case. Step 3 in the yellow circle here is to find the total current. Well, it makes sense. Once you have the impedance, it makes sense to calculate the total current. So we take the battery, 10 at 0, at an angle of 0, and we put it in brackets, and we divide it by the total impedance. I challenge you to get the answer that's in red down at the bottom of this page. Go back and look at the last page. The next page, once you've got that, you find out that, well, this is not a series circuit. This circuit asks you to calculate all the currents. We know what the voltage is across the capacitor and resistors. It's the battery, 10 at 0. So There's no disputing that. We need to calculate the current. So if you look at the area here where the black box is, I go ahead and I compute Ohm's law for each of the 3 branches, and I notice that the largest current flows through the smallest resistor. That makes sense. A parallel circuit, the smallest resistor gets the lowest amount of current. 10 milliamps to be exact. If you got 10 milliamps, good for you. Move on to the next computation. If you take a look at resistor 1, it's twice the size of resistor 2. So therefore, it runs at half the current, and the computation shows that out. And last but not least, the capacitor's voltage is divided by the impedance of the capacitor at minus 90, and we end up with this answer in the blue circle, 6.28 at an angle of 90 milliamps. If you've gotten that far, you've solved your first successful parallel circuit. I want you to look at the recipe. How did I lay it out? How did I label everything? How did I have the patience to do this? And last but not least, check it. Run a check of the total currents, because the battery is going to supply this 16.262 milliamps. That is what the total current comes out to, right? But we want to be able to take that 16.262, and we want to be able to add the resistors, and we want to be able to add the capacitor and get the proper answer. So can you get this answer in the green box? If the answer is yes, congratulations. You are pretty close. Pay attention to the fact that your voltages and your currents will be slightly off, but extremely close. The last 2 pages are left for your dissection. Here's where you get to show your mettle. I've taken another circuit here, and I have broken it down into this module in green and converted all the resistors and inductors in this case to boxes. This is the safest way to do it. Label them impedances, X sub L1 and X sub L2, and proceed to crunch. As was the last problem, calculate your X sub Ls, and then calculate your total current in each component on the last page here. And last but not least, calculate the current in the remaining resistor 1. Now I want you to notice that in this problem, we kind of went a little bit different order than we did with the capacitor resistors. I solved the 3 currents first. You know why? Because you can. If you have all the elements of current, which is voltage and resistance, voltage and impedance, voltage and reactance, then you're welcome to calculate the 3 currents like we did, finished off on the top of this page. And finally, out of sequence from the last problem we worked, we came through and calculated total impedance. See if you can get this calculation in blue done in one step. A tip: you've already done this calculation for the capacitor circuit you just finished. See if you know how to go into your calculator, edit the numbers, but leave the brackets and leave the division in place so that you don't make as many mistakes the second time, and see if you get 204 at an angle of minus 78.18. Last but not least, we could have calculated this a long time ago if we'd have just calculated the impedance. but we left it for last and show that the current in this circuit is 24.40 milliamps at minus 78.18. Fantastic, fantastic. We can finally take Kirchhoff's current law, which says the sum of the currents is equal to the total coming from the battery. So when a circuit is connected to a battery, all the current that is required of the resistance, of the impedance, of the reactance, whatever it is you've plugged in, it will flow through the three chambers of parallel circuits. And as you can see, our cross checks come out fairly accurate. So run off, review these two problems, head to your homework. You are now 2 out of 5 weeks into your learning curve. And congratulations if you've gotten this far. You're tough, perseverant, and you want to succeed and be the best you can be. I congratulate you.